My interests in fuel cell technology go all the way back to my introduction to energy systems by one of my mentors at the University of Victoria, David Scott, who pointed out that fuel cell technology, one of the most promising technologies for electrification of transport, is a technology that relies very heavily on fluid mechanics, heat and mass transport, what we refer to as transport phenomena. And I happen to have expertise in those areas, but I had never actually applied it to electrochemical energy conversion systems. And it appeared to be a very worthwhile and exciting avenue of research, and so that's how I started working in that field about 20 years ago or so. One of the key challenges that we have currently regarding the energy system is the transport sector. We need to move from fossil fuels to low carbon or zero carbon sources, and one of the best ways of doing that is by electrifying the transportation sector. You can do electrification either through batteries or fuel cells. These are the two main contenders, and they have advantages and areas where they're most suited for. Fuel cells are very well suited for long-distance driving, for large vehicles, for situations when one doesn't have access to quick recharging facilities, etc. So fuel cells are essentially electrochemical energy conversion devices. The main difference with batteries is that they allow you to actually produce electricity and drive your powertrain as long as you have a fuel on board. The fuel of choice for fuel cell technology is hydrogen. With hydrogen, you combine that with air, or the oxygen from the surrounding air, and you essentially produce electricity and clean water. Now, fuel cells operate on the basis of electrochemical energy conversion, so there is a reaction that occurs within the system. With that reaction, you're also evolving heat. In order for the reaction to take place, you have to provide fluids or gases to react, and namely hydrogen and oxygen. And you have a whole array of so-called thermofluid transport phenomena that occur. And it's a kind of thing that mechanical engineers and chemical engineers in particular learn quite a bit about in their undergraduate and graduate programs. And so what we're trying to do is actually understand how these mechanisms of heat transfer, mass transfer, fluid flow, electrochemical reaction, etc., combine together to bring them together in as efficient a manner as possible to make sure that the fuel cells operate efficiently and that they maintain long durability and lifetime in the process. So the fascinating thing about fuel cell technology is not only this array of heat, mass, charge, transport, and electrochemistry that occur all together to make this sort of reaction happen and produce electricity, but there is also a variety of materials that you have in the system that allow you to produce electricity. One of them is a polymer membrane. It's essentially an electrolyte that allows the transfer of protonic charges. The other is the electrode, which has a very thin, nanostructured catalyst layer. This electrode or catalyst layer is one of the core components of fuel cell technology. So it's a porous media. It's a composite media that consists of carbon, a polymer that has special properties, and platinum. All of this in a very, very thin layer that's something of the order of 1/10 of a millimeter in thickness. and with very, very tiny pores that allow the transport of reactants. So if you will, that's almost kind of like the alveolus in the human body, where you're breathing oxygen and you're then transporting that oxygen to the bloodstream. The catalyst layer needs to be fed oxygen and combines that oxygen with the hydrogen to produce electricity. In the process, you're producing heat, you're producing electricity, and you're producing water. And you need to manage all of these components for the system to work effectively. So we're currently at a watershed with respect to fuel cell technology. Most auto manufacturers in the world have fuel cell programs, and in fact, the Japanese and Korean auto manufacturers have started last year a lease program that puts in the hands of regular drivers and customers fuel cell vehicles as long as you're in proximity to fueling stations. The next step is really the larger scale commercialization that's likely to start taking place in 2016 over a period of 3 or 4 years. Now, for that to launch successfully, car manufacturers need to, first of all, have longer durability fuel cell systems and cheaper fuel cell stacks. That can be achieved in part by reducing the platinum loading, but also through mass manufacturing. And all of these things are coming along nicely together with sort of more or less an objective towards perhaps 1 million fuel cell vehicles a year worldwide in around 2020 or so. That's going to be a very significant advancement because with fuel cell vehicles in conjunction with hydrogen technology, we have one of the most attractive pathways for long-term sustainability. In order to achieve sustainability in energy systems, we need to shift from high carbon sources to low carbon sources. And fuel cells allow you to do that in conjunction with hydrogen by essentially producing hydrogen through hydroelectricity, through renewable energy such as geothermal, wind, or solar energy, using the process of electrolysis to produce hydrogen and then feeding that into your fuel cell vehicles. So that's really, in the longer term, the most exciting prospect is this electrification and decarbonization of the transportation sector that's going to help us towards a sustainable energy future.